Okay, next is radioactivity. Yes, what is radioactivity? One of the most important part of your chapter. What do you mean by radioactivity? See, out of 208 known nuclei, sorry, out of 1500 known nuclei, 200 are stable, 208 are stable. Remaining unstable nuclei radiate some amount of rays to get stable, and that phenomena is known as radioactivity. I repeat, among 1500 known nuclei, 208 nuclei are stable. Remaining other unstable nuclei, they will undergo decay process, and this phenomena is known as radioactivity. Which type of decays it will go? It will go to decays like alpha. It is also known as helium nucleus decay. Beta. In beta we have two types: beta positive, beta negative. Beta positive known as positron, beta negative known as electron. Okay. Then third will be gamma rays. Okay, beta decay, alpha decay. With that, compulsion will be of gamma decay. Let's see each thing one by one. So, what will be the unit of radioactivity for everything? You see, physics is all about the measurement. So, for radioactivity also, there is a unit, and that unit is becquerel. Becquerel. Okay. So, in 1896, radioactivity was accidentally discovered by Henry Becquerel. Becquerel noticed an intriguing phenomena while researching the fluorescence and phosphorescence of substances exposed to visible light. He used visible light to illuminate few pieces of uranium potassium sulfate, then wrapped back in black paper and used a piece of silver to divide the package from photograph plate. When the photographic plate was developed, that must have been released by the compound and was able to pierce both the silver and the black paper. According to the later experiment, radioactivity is a nuclear phenomena caused by disintegrating of unstable nucleus. In nature, there are three kinds of radioactive decay: alpha, helium nucleus, then a decay which is an electron or positron, that is beta decay. Sorry, that is beta decay. Okay. Sorry. Yes. Okay. Beta decay and gamma decay. Alpha decay, beta decay, and gamma decay. A decay which releases high energy photon, hundreds of kilo electrovolt or more. These are gamma decays. Now what? Okay. So those were radioactive substances. Let's see each thing one by one. Yes, types of decay. I'll explain each thing one by one. Okay. First of all, types of decay. There are three types of decay. We'll see each thing. Is types of decay. First is alpha decay. Okay. Alpha particle is helium nucleus. First point. Remember, alpha particle is helium nucleus. Second, mass is equal to 4 atomic mass unit. And charge will be plus 2e. Third thing, third thing, element A to Z. From this, if helium is released, check, helium is released 4 and 2, then we will be left with only what? We will be only left with daughter nuclei, and that daughter nuclei will be A minus 4 and Z minus 2. See why this? Because sum of atomic number and mass number at both sides should be same. If A is 16 and 4 is released, there should be something to balance this A. So that whatever the value will be, that value should be so such that if we are adding this part and if we are adding this part, it should be same. That means, see, if A minus 4, if it would be 20, if A is 16, this is 4, and this would be 20, 20 minus 4 would have given us what? 16 only. Okay. Let us consider an example. Example is we have a uranium with mass number 238 and 92. From this, we are releasing helium. Helium will be 4 and 2. What we will be left with? We'll be left with thorium. Thorium means what? 238 minus 4. That will be 234. 92 minus 2. That means that will be 90. See, the first thing I will mark it with blue pen. This is known as parent nuclei. This is your alpha particle. I'm marking here. Alpha particle. And this part, this part is known as daughter nuclei. We don't have sun nuclei, okay? We only have daughter nuclei. Once again, first will be what? First will be parent nuclei, this will be alpha particle, and this will be daughter nuclei. Parent, alpha, and daughter. This is the first type. The first type means what? First type means it will be decay, alpha decay. Okay. Why this decay is happening? See, we'll take neutron to proton ratio. If I take neutron to proton ratio before this, it will be it will be 146 to 92. Check. This will be 1.58. This is not stable. See, there will be fluctuation something. So what if we are taking the ratio of neutron to proton? So here it will be 144 upon 90. If it is 144 upon 90, it will be 1.6. So it will be stable. Previously it was not stable. Now it is stable. Okay. So this is why alpha decay process is happening. Okay. Yes. Let's see the next one. Next is beta decay. Next we have is beta decay. And how much energy is released? Yeah, let's see how much energy is released. Standardly, we have X A to Z. From this, what we are removing? Helium 4 and 2. We will be left with Y. And we will be left with Q. Okay. What is mass defect? Yes, we know what is mass defect. Delta M is equal to mx minus m alpha plus my. What will be energy released? Energy released will be A is equal to mc square. Mx minus m alpha plus my. We know what value of c square. What is c square? We'll write this same as it is and we will multiply it by 9.315 mega electron. Okay, that will be our radioactivity. That process is our radioactivity of alpha particle. Now we'll see for the beta. For the beta, very important, beta particle, beta decay is very important. Okay, beta decay. See, in the process of beta decay, in the process of beta decay, we have two things: beta negative decay and beta positive decay. Okay, in beta negative decay, we are releasing electron. In beta positive decay, we will release positron. Electron and positron. Okay, yes. First, or beta. Okay, in beta decay, here mass will be 0. Here your mass will be 0 and your charge will be minus E. Okay, so it will be x a to z. It will be from A to Z. Electron will remove, that means this will be removed, plus Y A Z plus 1 plus V bar. This is anti-neutrino. See, what is V bar? V bar is anti-neutrino particle. Previously it was not there, only there was a heat form. See, again this is parent, I'm marking. First, this is parent. This is beta negative decay, also known as what? It is also known as electron. This is daughter nuclei. And this is your anti-neutrino particle. It will be represented by V gamma, V dash, V dash. Okay. See what is happening here. Here, what is happening? Just understand what I'm saying. Here, beta decay is a conversion of neutron to proton. It is a conversion of neutron to proton. How it is, how there will be the conversion, just understand. You understand this equation? See, in this equation you have a x z, you are releasing this thing, so a minus 0 will be a, z minus minus 1 will be z plus 1. So here if you take the example, if you take the example of carbon, we have 14C6. From this we are releasing beta negative decay. So carbon, if from carbon, if beta negative decay is released, that means this will be 14, 6 plus 1 will be 7, and there will be the release of antineutrino. Actually, in beta negative decay, I repeat my sentence, there is a conversion of neutron into proton. How neutron into proton? Just understand. Now, see, I am writing here. Actually, in beta minus decay, there is a conversion of neutron to proton into nucleus. Okay. This is neutron. From this we are releasing, we will be left with proton 1 plus 0 1, 0 minus minus 1 will be 1 plus V bar. During beta negative decay, mass of nucleus remain unchanged. See here what is happening. Check. There is a conversion of neutron to proton. Okay. Here nucleus, the mass of nucleus remain unchanged. Z increase by 1 and N decrease by 1. Z increase and N decrease. Total will not change. Z will increase and N will decrease. Okay. A will not change. Z will increase and A will decrease. Sorry, N will decrease. Okay. Yes. Next, same thing. Yeah. Next we have beta plus decay. We have beta plus decay. I will use the same marker. I just have to make some manipulation. So here I will mark it as beta plus decay. If it is beta plus decay plus 1 plus 1, it is known as positron. Mass will be 0, charge will be plus E. Okay, here it will be plus 1, so here it will be Z minus 1. Sorry, there it was anti-neutrino, here it will be neutrino. Actually in this process we are converting proton into neutron. There was a conversion of neutron to proton. Here we are converting proton to neutron. How that I will explain. See, I am changing the marker. Yes. So here what we have, I'll take some other example. In this example we have, in this example we have 12 and 7. From this it is released plus 12, 7 minus 1 will be 6. It will be there plus V bar. Actually in beta plus decay there is a conversion of proton to neutron. Into nucleus. Okay, then what we have, Then we have 1p1. This is released 0 plus 1 plus 1 n 0 plus v bar plus q. Okay. Then last we have gamma radiation. What is gamma radiation? Gamma radiation has been released. How it will be released? It will be released in the form of em minus en is equal to h gamma. That gamma will be equal to em minus en upon h. This is how the radioactivity process works. Let's see some question based on this. Yes. In beta decay minus decay, what will happen? Yes, I'll not tell. You will say what will happen in beta negative decay. Neutron to proton, beta negative decay it is. So in beta negative decay, what will happen? Neutron to proton will happen and anti-neutrino will happen. That means which option will be the right one? A. Neutron convert to proton with the emission of anti-neutrino particle. Let's see the next one. When radioactive material decay, which of the following substance cannot be released? Cannot be released. Proton are not released. Okay. Let's see the next one. What kind of particle does a radioactive element release during beta decay? Positron and electron, two proton and electron, one electron, none of these. Yes, obviously the answer is A, positron and electron, beta plus beta minus decay. What is the process in which an unstable nucleus transforms into stable one by emitting radiation? Unstable to stable. Which will be the process? Yes, that process is a radioactive process, radioactivity.